So I'm here today to discuss green computing since Prashant is away. For those of you who don't know me, I'm a professor in the electrical computer engineering department, although I was previously in the CS department working largely with Prashant on topics, research topics in green computing. So today I'll discuss the general area of green computing, kind of its two different sides. So which are really the two parts are greening up computing. So this means kind of sustainable IT. You guys have probably maybe heard about kind of some power issues related to various, or even experienced some power issues related to like mobile devices, but this also extends up to more sophisticated hardware in data centers. So this is really about optimizing IT to reduce its energy impact and improve its energy efficiency. I'll also discuss computing for greening, which is kind of how to use IT, how to use computation to make physical infrastructure more efficient. So this is kind of infrastructure in homes, offices, buildings, transportation. So I kind of discuss these two parts somewhat separately, although there's correlations or relationships between the two. So the first part, greening of computing. The area of kind of improving the energy efficiency of computation is, been around for a long time. It's primarily been the subject of work related to mobile devices, kind of starting in the mid to late 1990s, even before kind of smartphones, just like PDAs and things like this. So improving their battery life, making them last longer, and also in terms of laptops. So other types of mobile devices like laptops, integrating more efficient energy efficiency optimizations into laptops to extend their battery lifetime. Recently, meaning within the past 5 to 10 years, with the growth of data centers, this type of work is kind of extended into optimizing kind of ensembles of machines or ensembles of servers in data centers. This is largely different than kind of optimizing the energy use of a single device. A data center is a large collection of machines, and also it's extended into optimizing other parts of a data center. For instance, its cooling costs and how it, what kind of servers it uses to actually process data in an efficient manner. So we'll look at today kind of energy efficient server design, what makes a server energy efficient. And the cost here, or the motivation here is a little bit maybe more significant than kind of like, just the convenience of having a longer battery life on your mobile phone or a longer battery life on your laptop. Data centers are expanding so rapidly, they're actually consuming an increasingly large fraction of society's entire energy consumption. It's actually not an insignificant fraction, and it's one of the most rapidly growing industries in terms of energy consumption. So actually, optimizing these data centers can have an actually big impact on carbon emissions. It can also lower its costs. So generating electricity to power these data centers and to cool them is also a significant part of its operating cost. At parity, really, with the cost of actually buying the servers is the cost of actually powering them. So we'll look at some of these issues today. So just some numbers here, and this is kind of not necessarily data center specific, just kind of IT in general. But if we look at kind of a general office building, okay, nowadays like a bank or even like an academic building like this, you can see upwards of 20% of its power usage goes to IT equipment. So servers in the building, various desktops in the building. A typical desktop, if left on all the time, will use between 100 watts and 200 watts. And if you scale that up, that's quite a bit of power. There are some recent studies, I'm not sure how accurate they are, but they were saying at kind of a large college research institution like a UMass, I think these numbers are actually coming from UCSD, that between actually 50 and 80% at a college is doing a lot of computing, like in its engineering department, its computer science department, that 50 to 80% of the energy can go towards IT. And then I was saying before, this is actually becoming a significantly larger fraction of society's energy use. So I think this number here, 3% of our carbon footprint and growing. I think not sure where the 3% number is coming from for carbon footprint, but I believe that 3%, the current estimates are 3% of our electricity consumption in the U.S. goes specifically to data centers. Okay, now these numbers here are just general IT, not just data centers like desktops, all the kinds of IT, the switches that go into powering, an office building or to supporting an office building. But today, roughly 3% and growing amount of electricity goes towards data centers, and I believe the numbers are around 0.3% of energy production. So energy includes more than just electricity. Electricity is roughly kind of 40% of our society's energy use. You have other ways to use energy, like burning natural gas or energy in your cars and whatnot. Yeah, so mostly what I'll talk about today is data centers. They're the largest fraction of the IT carbon footprint, and more IT is moving to data centers, moving to the cloud, and going away from kind of desktop local energy use. So what is a data center? So in this class, have you guys kind of discussed data centers, or do people have a general knowledge what data centers are? Okay, so I won't spend too much time on this. So, it's facilities, right, for housing large numbers of servers. So as just an example, data centers range in size from very small to very, very large. And people generally kind of call any kind of large collection of computers a data center, whether or not it's housed in a specific facility or not. So this is just an example ripped off kind of some of Google's web pages. So this one in Dales, Oregon, which is pictured there, kind of in the small picture, is roughly 12 times the size of a football field. It's built in Dales, Oregon, because it's near a hydroelectric plant. These data centers are typically sited because of their power demands, because the power is such a large part of their operating costs. So they want cheap power, and they generally want cleaner power, at least from a public relations standpoint. In this case, this data center is using roughly 100 megawatts of power, which is enough for a small city, and potentially can have 100,000 servers with many more cores than that per server. So I was saying power usage has become a big concern in these data centers, and it's receiving some unwanted attention. So actually in this is September 22nd and the 23rd, yeah, the 22nd and the 23rd, the New York Times actually ran a front page cover story on data center power usage, and kind of how significant it is, and also some behaviors that data center operators engage in with local utility companies to try and negotiate for really cheap rates. So there were some kind of nefarious practices that these articles are pointing out. So if you're interested more in kind of these articles talking about some of the politics, but also some of the impacts of data center power consumption, these articles are online and you can go see them, but it just is an example of how this kind of power usage has actually kind of been brought into the mainstream. That it was on the cover of the New York Times, 22nd and the 23rd. So this was a fairly large piece for the Sunday magazine and the Times. So if we assume kind of 100,000 servers in a data center, we kind of just do some rough estimates here. The monthly cost of one server, if we assume it's 500 watts, this is kind of a large server like a Xeon multi-core server. And then we look at that number of watts times a certain cost per kilowatt hour, let's say 10 cents a kilowatt hour, which is roughly the price you guys probably pay for your utility bill. Data centers obviously are large consumers. That article, if you read it, points out they engage in negotiation tactics to get special rates. But if we just assume a normal rate of 10 cents per kilowatt hour, and we leave that server on for the whole month, we're going to get roughly a cost of $50 per server. So at 100,000 servers, you're looking at roughly $5 million cost per month just to power the servers. Okay, now powering the servers is actually just a small part of the power consumption. You also have to power all the auxiliary things like lights. In addition, you have to cool the servers. Okay, so So what about the cost of cooling? Well, an efficient data center today, you roughly add about 20% to the bill. Normally like maybe 4 or 5 years ago, this was roughly 100%, meaning you would double the cost to cool. So the amount of electricity it takes to cool, for an efficient data center, it's going to be about 1 million, an additional 1 million on top of your 5 million. For an inefficient data center, it could be another 5 million on top of your 5 million. Okay, and we'll discuss some ways recently the data centers have new design techniques they've used to reduce this cost. Yeah, so it's significant, 6 million for an efficient data center, maybe 10 million for an inefficient one. So this pie chart here kind of breaks down the costs into different categories, so the monthly cost. So here, this is using kind of a different method than this was kind of back of the envelope here. This here is actually taken out of a relatively well-known blog posting by one of the guys who is head of Amazon's kind of data center power infrastructure. Okay, and so he broke it down, based on kind of what he's seen, in the industry. So he breaks it down to kind of 4 categories in terms of monthly cost for power: servers, power and cooling infrastructure, the actual power. So this is the cost to buy servers. This is the amortized cost to actually build the power and cooling infrastructure. So actually, purchase and install all the HVAC equipment, run all the wires, maintain, like if you have co-generators that, for backup power, UPSs for backup power. The green is actual power costs that you're using, and the other blue, this darker blue, is just other infrastructure, presumably like lights and other just auxiliary infrastructure in a data center. And what you can see here is that the power-related costs are roughly the same as the server costs. Okay, so the cost to buy servers, amortized over a 3-year server lifetime, is roughly equal to the cost to build the power and cooling infrastructure and maintain it, and to purchase power to actually power the servers. Okay, and then these costs, these costs here, these costs are kind of constantly changing based on more efficient server designs that are coming out, and more efficient design techniques for kind of cooling them. But these costs here are also changing in terms of, if electricity prices are going up, labor prices are going up. So there's some flux here, but it's roughly at parity. In general, the thought is that moving forward, these power costs will eventually come to dominate the server costs in terms of like hardware. Servers kind of constantly getting cheaper, although we're reaching the limits of their power efficiency.
What is the monthly cost of servers? Like servers you buy only once?
It's amortized, so it's amortized over a 3-year server lifetime, and it's amortized over a 15-year infrastructure lifetime. So like, what he's saying is like, okay, the power and cooling infrastructure, you build once, right? You build the building one time, but it's a massive cost, right? And so he's amortizing that cost over a 15-year lifetime. The servers you buy, let's say once every 3 years, the servers get old, he's amortizing the servers over a 3-year lifetime. So how do we talk about kind of data center energy efficiency? The typical metric is called PUE, power usage effectiveness. So what PUE is basically, your total facility power, how much power is coming kind of off the grid into your facility, or wherever you're getting the power from, divided by how much power is actually being used to power servers. Okay, so like I was saying before, a few years ago, a PUE of 2 was common, which means that for each watt of IT power, there was an additional watt consumed in overhead, largely for cooling the servers. Okay, but there are some other things. This is generally how you talk about it. If you go to different company websites like Google or whatever, Apple, they actually generally will have some statistics on their PUEs. Now, there are some evolving standards for how you compute PUE. This looks very simple, but since to get total facility power and IT equipment power, they have to aggregate a lot of metrics. Different companies actually have slightly different ways of computing this, so it's still kind of an evolving standard for how to do this. So we'll talk about a few ways to get low PUE design, so essentially more efficient data center design. So the 3 ways we'll cover it here are a better power infrastructure, more efficient power infrastructure, better air conditioning, how can we make more efficient use of the power used for cooling, and then better server and IT equipment. How do we make servers, what are the general methods for making servers more energy efficient? So in terms of power infrastructure, I won't go into it too much, but there's been a lot of research work recently on using energy storage, variety of different types of energy storage to do some intelligent load shifting. So since electricity prices kind of vary based on demand, actually they can vary hourly, they can also vary kind of at 5-minute intervals. You can use energy storage to shift load around to when there's going to be low price periods. You can also use, since data centers are typically part of geo-replicated applications that replicate data across data centers across the country and the world. There's also been a lot of work on kind of especially in terms of content distribution networks, redirecting requests to data centers that have at that particular moment either the cheapest or the greenest power. Now obviously you have to keep into mind the latency requirements of your application and how far away a data center is, and so a lot of that work is kind of dealing with some of those complexities. Yes, so what makes a lot of this potentially practical in data centers, despite the high cost of energy storage, is that many of these data centers already use a lot of energy storage for a couple of reasons. One is to condition power. So servers are, sensitive electronic equipment, okay? And so the electric grid, can experience outages like unplanned. They can also experience, voltage spikes or dips that could harm the electrical equipment, okay? So oftentimes, data centers will run power, grid power through UPSs, kind of online UPSs, batteries, to condition it, so that on the output, basically you get a very tight, AC sine wave, okay, that has very little variation, no voltage dips, no voltage spikes. If there are outages, obviously these online UPSs switch power to the battery instantaneously so that the servers remain running. Oftentimes, data centers have on-site generators, which they spin up if power goes out, so they continue operations despite the loss of power. Okay, so they're already using a lot of energy storage for these purposes. As a result, they just have it sitting around. So shifting load is just one more way to use this energy storage to lower costs. Okay. The other thing they can do is be more efficient about how they use power. So there are a couple ways to be more efficient. One is that in normal data centers, a few years ago, and even today to a large extent, what would happen is you would potentially bring in power from the electric grid, AC power. Okay, you guys know the difference between AC and DC power. Bring in AC power. You would run it through these online UPSs to condition it. Out the other side, so that converts it to DC, right? You get some conversion losses there. Out the other side comes AC power again, runs through the data center, and then gets converted back to DC to power the servers. And there may be some voltage drops in between there because you have high voltage coming off the line, and various places has to be converted to lower voltage. Ultimately, 120 volts kind of out the wall is what a server plugs into, and its power supply expects. So there have been people who have advocated the use of more DC power, so actually building data centers with DC power throughout. This would prevent the conversion losses at the power supply and the servers, and it would also prevent these multiple conversions, which you're losing maybe 10% per conversion. The MGH PCC, which I assume you guys are familiar with, the data center down the street, what it actually does is it runs kind of the high voltage to the to much closer to the servers rather than kind of stepping down voltage right at the inset. It runs them very close to the servers. It actually doesn't need power distribution units as a result of that. There's some other ways you can do this. If your data center is using multi-phase power, so typically power that comes into a data center is three-phased, so it's basically three kind of overlapping, AC signals. It turns out if you balance these phases, balance the electricity usage of each phase, then you can get additional gains. That it's more efficient through the magic of electricity if you balance each phase. Basically, you by balancing each phase, you eliminate return current on the return wire. And then finally, the final way kind of here is to use more flexible and less redundant systems. So typically, the power infrastructure for a data center is highly over-provisioned. Okay, so just like anything in computer science has been over-provisioned, if you if you pack more into it, operate closer to the red line, then you can get more efficiency. So in this case, what many people have advocated is actually oversubscribing the power infrastructure. So packing more servers into a data center than its actual power infrastructure could support if all the servers were operating at 100% utilization. Okay. The reason being that if you look at studies of data centers, all the servers are not operating at 100% utilization typically. Okay, as a result of this, the power infrastructure that's been designed is highly underutilized. Okay, so you actually could support multiple servers operating at 10 to 50% utilization. If the power infrastructure has been designed for servers operating at 100% utilization, you could pack in between 10 times and 2 times more servers. Now, of course, if the servers kind of all peak at the same time, you'd have to cap their power in some way. But it turns out you only have to do that briefly based on kind of statistical studies of actual data center usage in Google data centers, Facebook data centers. So that's just kind of some of the research topics in this area. Yep.
So I didn't quite understand what is the advantage of using the high voltage close to the servers in the MG-PCC trees.
Because you basically, for every time you step down voltage, you get a 10% loss. Okay, so a lot of times normally what would happen is you would come in high voltage off the line, you would step it down once, it would feed into kind of either power distribution units or battery arrays, and then it would be stepped down again. You're basically removing that first step down in voltage, so 10% usage. So I'll just briefly mention a bunch of kind of better air conditioning improvements. The first one is hot aisle, cold aisle containment. So if you go to the MGH-PCC, you'll see this. And the idea here is to separate servers from their exhaust air. So basically, you enclose servers in a box. The racks, are facing. This is the exhaust flowing out. They're inward facing. You cool inside of here. You don't cool outside of here, and you let the exhaust air just come out and then get vented out. Okay, so you separate the cold from the hot air. Eliminate hot spots. So actually balancing your load evenly across the data center is better. For instance, these cracks, which are essentially the air conditioning units. Okay, just like at your home, there are certain places where the air conditioning comes out, like over there, right, in this room. And there's a sensor that's measuring this. Okay. Well, if you have a hot spot near that sensor, then that unit is going to think that it needs to cool this space, much more than it actually does. Okay. So the idea is to balance load across the data center such that these air conditioning units, you can reduce the cooling of these air conditioning units so that it doesn't overly cool based on some sort of hot spot that it senses that's only in one localized part of the data center. So you can see kind of these hot spots here. So this can have a big impact on cooling costs. Another efficiency improvement is just using outside air to cool your data center. So this is called air side economization. So it's actually units that kind of suck in outside air to cool the data center and extract also extract the heated air. This would advocate building data centers up north. So this is actually a a heat map that one of these companies has released of where you can build your data centers to get good airside economization. This is a web page off Iceland's like tourism or something, or industry web page. It says Iceland, an outstanding location for data centers. So Iceland's actually good not only because it's cold, but Iceland is a big place for geothermal energy. So energy is also very cheap and clean in Iceland as a result of that. So it's cold, energy is cheap and clean. It is a good place for data centers, as they like to say. The extreme part of airside economization is actually just putting servers outside. So the airside economization units actually kind of filter air and do have fans, whatever, to suck air in. Microsoft has actually, and some other companies, that actually experimented with just kind of putting the servers outside. Generally, I think the results were fairly successful in the sense that even when it got really hot by kind of normal standards, like 100 degrees outside, 110 degrees, servers were able to operate relatively normally. So a lot of people have taken these experiments and kind of advocated raising the temperature in data centers, so cooling them less. That they don't need to be operated at 80 degrees. You could raise the temperature inside the data center to 90 or 100 degrees, assuming that you don't have people kind of working in the data center will pass out or something. But these guys basically ran this. These guys from Microsoft ran this experiment, to see how you would get to a PUE of 1, basically just removing cooling costs and seeing how feasible that was. And what they found was problems were not temperature related, meaning on hot days their servers didn't generally fail, but there were kind of filter related problems, meaning that they would suck in kind of leaves and other things. They probably should have contained it a little more. So that covers kind of the different aspects of better air conditioning. So I'll also talk about building more efficient servers and IT equipment. So this kind of gives you a breakdown of kind of what uses power in the data center in terms of IT equipment. So servers are the dominant power consumer, about 65%. Storage, about 21%. And networking, about 9%. So this is all the switches kind of in the data center. As a result, we'll talk about storage first. So ideally, servers would be what's called energy proportional. So this means that their power usage would scale linearly with their workload's intensity. So if they're at 100% utilization, they use some number of watts. Then if they're at 50% utilization, they would use half that number of watts. Okay? And an ideal, an idle server, obviously, would use 0 watts. Unfortunately, servers are not energy proportional. In fact, they're very far from energy proportional. When they're idle, the best servers use about half of their peak power. So rather than using kind of 50% or M over 2 at 50%, they're using M over 2 at idle. Okay, at 50%, and then it roughly scales linearly from there. So at 50% utilization, they're using about 75% of their peak power. Okay, so why are they not energy proportional? CPUs generally are close to energy proportional. They're not quite energy proportional, and it's improving. There are a lot of CPU power states that are used in HPI that kind of ramps CPUs up and down. Not only in terms of, whenever a CPU is halted, it's using less power, but there's also dynamic voltage and frequency scaling that scales the speed of the CPU and its voltage, as its utilization increases and decreases to scale its power usage. Unfortunately, there are other components that consume power. The disk, RAM, the motherboard, the network card all also consume power. So this is just a breakdown recently of one CPU. Or one platform. CPU using about 33%. The red is memory is kind of another big chunk. Disk. This is the other is generally the power supply, which I don't have a slide on, but the power supply also uses some power, essentially in that conversion of AC to DC inside the box. Actually, it's less efficient at lower utilizations. And then the networking, the NIC card is just a sliver. So CPUs have been improving. Unfortunately, because CPUs have been improving, this piece of the pie has been getting smaller and smaller, which actually means that the CPU is becoming less and less important in terms of energy proportionality. So in terms of proportionality, making the CPU kind of more efficient actually is making the problem somewhat worse, even though it's decreasing the total power of the machine. And these other components are not really getting much better. So that's proportionality. So unfortunately, servers are not very proportional today. So efficiency is also very important. So by efficiency, I mean how much work, computation are you able to do for every joule of energy used. Okay, so this is different than proportionality. You can have something that is highly inefficient but very proportional, or vice versa. You could have something that's highly efficient but not very proportional. Okay, so like something that's highly proportional but not efficient would use a ton of joules for each work at 100% utilization, but at 50% utilization it would use half that many joules. It would still be inefficient because the work, even though since it's scaling linearly, the work done per joule would be the same. Okay. The bad news here is that servers are also not very efficient generally. The reason for this kind of is cited in some of these surveys here is that servers are rarely kind of completely idle. In fact, most of the time their load is around like 30% in this. This is from a Google paper, a Google data center. And so this graph here is kind of just bucketing the fraction of time servers are at different utilizations in a Google data center. You can see, most of the time they're either kind of close to idle but not quite idle, and around 30%. And they're rarely kind of fully at 100% utilization. Okay, now the most efficient operating point is 100% utilization. Okay, because since they're not energy proportional, you basically want to be at 100% utilization all the time. If you're at 0% utilization, you're completely inefficient. You're doing absolutely nothing, but you're just burning lots of power. Okay, you're infinitely inefficient. Okay, and so at 100% you're the best, but you're rarely at 100%. Since you're rarely idle, you can't just turn them off. They have to stay on to serve as kind of brief periods of utilization. Okay, so over here you can kind of see this graph of kind of energy efficiency versus their power use. And as you can see, kind of the efficiency, the work done per joule is maximized at 100% utilization, and it kind of degrades from there, tails off from there fairly quickly due to this lack of energy proportionality. And so this 30% utilization range is right in this spot where it's starting to tail off and be really inefficient. As you can see here, this red line goes down here to infinity. There's an asymptote here because when you're doing nothing but using a lot of power, then that's infinitely inefficient. Yeah, so unfortunately servers are not very efficient. So the reasons for the inefficiency, a lot of times there are lots of unused CPU features. Really complex CPUs have really large caches. They have complex architectural features like different forms of like pipelining, hyper-threading that are trying to exploit instruction level parallelism. And these components, even if they're not used, they're always on and they're always using power in the CPU. And obviously higher frequency CPUs, frequency is directly proportional to power usage. So the higher the frequency, the more power that's going to be used by the CPU. So one thing that people have been looking at as a way to kind of make servers more efficient, actually, for workloads where the CPU is not the bottleneck, don't use really complex, high frequency, high power CPUs. Okay, so like for a lot of data center workloads, the disk is the bottleneck. It's a data center, they operate on large quantities of data, like all these big data platforms. They're reading lots of data from a disk, and they're writing lots of data to the disk, right? And the amount of computation they do on the data pales in terms of time, pales in comparison to the time they spend reading and the time they spend writing. Okay, and so as a result of this, basically people have said that you don't really need for these specific kinds of workloads, a really high power, efficient CPU. Well, I shouldn't say efficient, a really fast, high power CPU. Rather, you could have a very low power, kind of slow CPU, something like you would have in a laptop, like an Atom processor or something, or even a cell phone, and that those CPUs are fast enough to, basically sustain the data read and write rates that these applications need, and also, do the computation necessary such that the CPU is still not a bottleneck. Okay, so it turns out that these kind of platforms can be very energy efficient because they're not wasting power anymore, just powering unused features of this CPU. So if you could kind of just general research on what's called balanced systems, this is what the approach that they adopt. Sometimes they adopt it for energy efficiency. Other times they adopt it just for kind of raw speed, so that you can fit more data center, more servers into the data center. Yeah, so like I said, it's always best to be at 100% utilization. Okay, regardless of even if you have these more efficient balanced systems, you still want to be at 100% utilization because your balanced system still is not energy proportional. Okay, so you always want to be at 100% utilization. If you're still on, you're being wasteful because you're not energy proportional. And even if you're off, even if you're turned off, you're still being wasteful because people built this infrastructure for you, as a server, and you're not doing anything with the infrastructure. So you're kind of wasting the fact that, this infrastructure was built for you. And building the infrastructure is very expensive. Okay, so I mean, ideally, when people build the data center, they want it to be utilized 100% kind of all the time. So this is, doing this, making 100%, reaching 100% utilization or close to it, is strongly linked with software flexibility, which I'm sure you guys have kind of discussed in this class. So, virtualization, so that software is less bound to the hardware. The ability to migrate, virtual machines around, to pack as many virtual machines as you can onto a server, such that it reaches 100% utilization. Also software-defined networking, so that you have kind of the bandwidth within a data center to be able to not only move things around kind of flexibly, but also such that wherever you put things in the data center, if there are two VMs in a data center, that they can communicate with each other, at fast speeds. Okay, so it's strongly linked with software flexibility as well. So I'm sure you guys have discussed, virtual machines. Yeah.
So you mentioned that even if the machines are off, then you're being wasteful because you're not using the infrastructure. But I guess that there's not much you can do about it because it only depends on the arrival rate of new tasks to the data center. Given a certain arrival rate, there isn't much you can do about that. Right?
Well, I mean, what people do in that case, I mean, this is why Amazon started EC2, right? I mean, this is why you want to get statistical as much statistical multiplexing as you can amongst a number of different workloads. Okay, and so if you personally, the operator of the data center, don't have enough workload to maintain 100% utilization, then you're incentivized to outsource it to other people. So I mean, and so EC2, essentially arose because Amazon, like everyone, like the electric grid, like other data center operators, they provision their data centers for peak demand. Okay, they provision for the time of year when their workload is the most intense, where they have to meet demand and it's most critical. So for Amazon, this is Christmas time, right? So like they provision all of their data centers to satisfy the demands at Christmas. Okay, now the rest of the year is nothing like Christmas time. So their data centers, were largely idle. So I believe that was the original motivation for EC2, was that they wanted to they had all this, not only just, infrastructure, but also all this software, to control that infrastructure that they could outsource to other people.
Right. But in case you don't have enough demand, it does make sense to turn off the servers.
Yeah, if you don't have enough demand, it makes sense to turn off the servers, although you're still being wasteful. Mm-hmm. Because you're wasting the infrastructure. You can't dynamically make the building bigger and smaller. You basically, I mean, it is an issue. I mean, it's a big issue. Because typically you build these data centers and you don't fill them up immediately. So like, for instance, the MGH PCC, you guys know what that is, right? I mean, it essentially has no servers in it right now. So it's PUE, like, this is an issue. Because, at least in terms for like marketing, if, it's supposed to be this very efficient data center, but it's PUE now, if they're asked, it's infinite, right? They have this entire facility with all of its air conditioning equipment, lights, whatever, but hardly any servers in it, right? So, all of the energy coming into it, almost none of it's being used to power servers because there just aren't any servers there, okay? So, it is very wasteful. You build an infrastructure, and this is very common, it takes a while for it to get filled. It's not like it just gets filled on day one. And, you typically build it, since it's such a long time period, you build it larger than you just estimate what you think you'll need. You don't necessarily know what you'll need. So there's a certain waste in that. I mean, this is all why EC2 and cloud computing has arisen, really, because of the economies of scale of kind of extracting efficiency out of statistical multiplexing of a variety of workloads that individual companies often can't reach this kind of 100% utilization by themselves using just their own workloads. So server virtual machines, I'm sure you guys have discussed them, provide isolation between different virtual machines, allows you to consolidate workload by moving, providing mechanisms to move the virtual machines around. You can also use their resource management hooks, to affect power consumption. So you can, they give you these hooks to control like the allocation of CPU and memory to virtual machines can also be used indirectly to manage power. So if you cap the CPU usage, you effectively can cap the power usage in a similar way that dynamic voltage and frequency scaling is able to do. Obviously migration here enables policies where you can migrate virtual machines around so that you can consolidate them onto a small number of physical servers and then turn off the other servers, although this is wasting the infrastructure. Although keep in mind that you don't necessarily want to consolidate them all onto a very small subset of servers that are physically located near each other, because then you might get a hotspot, right? So there's kind of a balance between kind of spreading load out and also kind of consolidating load, but on servers that are kind of topologically different places in the data center so that the heat is actually balanced across it. As a result of kind of virtualization and this flexibility in software, what people have done since servers are not energy proportional is to build energy proportional ensembles or groups of data center or groups of servers to make the data center energy proportional even though the individual servers are not. The canonical way this is done is, as utilization decreases, you turn off components by migrating the workload onto a smaller set of active components, and as utilization increases, you turn components back on, servers back on, and you migrate the workload across the newly active components. There are issues with this, though. So some of the issues with this, so the workload may store local data on the component it's on, and so moving that data may take a long time. So you can't just, migrating the memory of a virtual machine may be fast, although even if it's live migration, the actual time it takes to migrate something could be on the order of minutes for a multi-gigabyte memory image. Turning on off the component itself might take a long time. It might take anywhere between 10 seconds if you're going into a sleep state, all the way to a minute or two if you're kind of physically powering down the server, like hitting the off button. The workload intensity may change faster than the data transfer. So the intensity of the workload may change much faster than you can transfer data to some other machine. It may change faster than you can turn on a new server. In fact, some of the data from Google said that servers are rarely idle, so there are actually fewer opportunities to do this kind of stuff while maintaining latency bounds for applications that are latency sensitive. They essentially need to always be on, to always be ready to service a request, within some number of milliseconds, and that, it's going to take you longer than milliseconds to either transfer data and turn on a new server and transfer whatever data needs to be to it, prime it for use. And this kind of approach also doesn't work if the workload is not distributed. So, this only works if you have a large distributed application where you can scale the number of servers in its active set. If you just have a kind of a single batch job, or you have just like a single web server, obviously, you know, this isn't going to work. You know, if it's just running on one or a few servers that are not energy proportional, then you can't really approximate energy proportional behavior very well. So beyond servers, other IT components are typically more inefficient than servers and less energy proportional, unfortunately. So servers are kind of like the best case. So switches and routers essentially use the same power at idle as they use at 100% utilization. So they're completely not energy proportional. Okay, so if they're doing nothing, they're using the same amount of power as if they're, you know, sending packets at, you know, as fast as they possibly can. Memory, you know, there are technologies where you can turn off memory banks. There are also technologies where you can degrade the quality, like the self-refresh rate of memory, which kind of degrades its reliability. They're rarely used. Okay, you rarely turn off memory banks. Memory is very hard to dynamically manage because memory usage changes so much within an application at different points in time. And actually, if you degrade the self-refresh rate of RAM, which kind of linearly degrades its or reduces its power usage, you actually have to modify your application significantly. Because if you know, most applications are written with the expectation that memory is correct. That when you store something in memory and you get it back out, it is what you stored in it. You know, and if you reduce its reliability by lowering the refresh rate, so that is not always true, or there's some probability that not being true that's greater than 0, then you have to kind of change the way you've built the application. So that's typically also not used, although there's some research in that area. Storage as well, you know, mechanical disks are not energy proportional, and it's very hard to make them energy proportional because actually spinning them up and down induces wear and tear on the read head. It's a mechanical component that, you know, has to actually move on the platter, has to actually spin. Those kind of mechanical components, you know, if you turn them on and off a lot, induces wear and tear. Okay, so I think some numbers are like, you know, roughly an old disk in a server could last, you know, 50,000 spin up, spin down cycles. So you can't do it too much per day, or you're going to degrade the reliability of your disks. On the flip side, flash uses nearly no energy and doesn't have efficiency. So a lot of people recently have become interested, a lot of companies have become interested in integrating renewables into their data centers for a variety of reasons. Public relations, there's a lot of bad press if you're using a lot of fossil fuels to power your data center. So Facebook and Apple have gotten a lot of bad press over the last few years for this. It's a hedge against electricity costs going up in the future, since once you install kind of solar panels or wind turbines, the electricity is free. And also, just in terms of this, goes with kind of public relations, being good citizens. Reducing your carbon emissions is kind of good for the environment. So this kind of stuff is actually happening in terms of integrating renewables into data centers. So this is a picture here of the iCloud data center that Apple recently built in Maiden, North Carolina. So co-located next to it is a 20 megawatt solar farm, which is quite large. And actually, I think they're planning on putting another 20 megawatt farm identical to this right next to it. So, you know, companies are kind of doing this kind of stuff. In this case, this solar farm requires about 171 acres of land, or 7.4 million square feet. Now, obviously, generating solar energy, you know, the energy density of solar panels is much less than the energy density of a data center, kind of per square foot. So, you know, to power a data center, you know, you need land area that's much larger than the data center to generate the solar for it. So that's why this is so large. In this case, it powers about 16% of the facility, although obviously solar kind of goes up and down throughout the day, so that's on average. In this case, on average, you know, 3.2 megawatts. The grid, you know, since it's going up and down, the grid has to absorb these variations because someone ultimately has to match supply and demand. The grid is able to do that kind of today because solar panels and intermittent, uncontrollable, renewable energy sources are not, don't contribute a significant portion of the electricity in the grid. But scaling this is a problem. So current estimates are that once solar and wind energy that are intermittent and uncontrollable become 15 to 20% of the grid's total energy generation, that the grid will not be able to match supply and demand anymore. So, these kind of large facilities, if they are to scale, they do introduce some problems.
So do you know offhand just a ballpark of about how much wind and solar as a percentage of our production are today?
Offhand. Yeah, I have those numbers. I don't think I put them in the slide, but it's like
0.1%, 1%?
it's like 1 to 3%.
Okay.
If you Google for Lawrence Livermore spaghetti diagram, that's I don't know. It's a common diagram. It actually breaks down breaks down the entire United States' energy generation and consumption by type. So it has nuclear, biofuels, wind and solar, all that. So yeah, I think it's 1 to 3%. We'd have to check that. It's not a significant fraction. So scaling this is a problem. And it introduces new dynamics. So if you can't just rely on the grid to balance supply and demand, you have to do some of it locally. Okay, someone has to balance supply and demand, right? Like instantaneously, the electricity generation has to equal the electricity consumption instantaneously, unless you have some energy storage. But energy storage is very expensive. So essentially, it can provide a small buffer, but it can't do long-term balancing. And also energy storage is very wasteful. Wasting between 20% for batteries. The only way to store energy at large scales is pumped water, so pumping water up a mountain and then using it later to power a hydro facility. By releasing that, actually has like about 50% waste of energy. So the best way to use energy is to use it immediately, and you obviously have to instantaneously match supply and demand. Someone has to do it. If the grid can't do it, then you need to do some of it locally. Okay, which means actually within a data center responding to these kind of dynamics where a cloud passes by and generation drops immediately. Okay. So that introduces new dynamics that people may not have considered as much in the past. It also potentially might require rethinking the PUE metric because you might care more about dirty energy that you're wasting than clean waste. Okay, so if you can use if you can't use clean energy at a particular time and you don't have enough storage to store it, then you just have to waste it. It's just burned out as heat or whatever. But really, if you've wasted clean energy, you're losing something, but it's not the same as kind of wasting dirty energy. Okay, so it may require rethinking that metric a little bit. So, any questions on any of the data center topics, or better air conditioning, better power infrastructure, better servers and IT equipment, and maybe integrating renewables? These are kind of the different ways to make data centers greener. Yep.
So this is kind of more of a software operating system question than a hardware type question. Sure. But I've seen something where I guess languages where application code would run in a virtual machine, like Java or Erlang or something. So I've seen for Erlang there was kind of get rid of the operating system and just run the VM as kind of super stripped down, just what the VM needs operating system. And then in that case, instead of putting up an EC2 server which takes minutes, it takes seconds. Is that a common trend, or do you see application code being closer and closer to the metal?
No? Well, certainly that improves agility, and that's certainly important. Improving agility, making things faster. Faster transition times can boot up and running. But I don't view those transition times necessarily as kind of they're important, but they're just one of many important aspects of performance. So the overhead of running a complete operating system, in terms of transition time, it is there is some overhead, but I don't view it as being that contributing that much to long transition times. I mean, obviously, the way EC2 kind of boots up a virtual machine, you could do that faster. You could, optimize that performance such that it would be close to kind of like, now obviously, the barrier there's going to be the memory image of the VM is likely going to be larger than the memory image of a Java virtual machine. So there's some fundamental, optimization barrier where a Java virtual machine, something stripped down like that, would be faster. But I wouldn't view it as, a huge win. Although certainly, there are lots of problems in this space, and that's potentially one issue that you could optimize. I do think that on the kind of like outside of the transition time, operating systems generally should be built to stay out of the way of the application. So in terms of their implicit overhead, in terms of like instructions they are running, if you're running some workload, let's say it's a Java VM Java workload written in Java, then I would expect that the Java VM would dominate would already dominate the CPU cycles of the machine, that the OS kind of, what it's doing outside of the Java VM shouldn't be, shouldn't contribute that much, that the Java VM should still dominate. So probably see, maybe some win in terms of transitions, although transitions are just kind of agile transitions are just one component of kind of that makes the system, that you can use for improving energy efficiency. In terms of like just while running, I'm not sure if it's a huge win. So the other thing is, just like physically powering a platform up. I guess if you optimize the platform just for Java, that could also be done quicker. But yeah, so it's a good point. Any other questions? No. So in the last, yeah.
So operating system overhead in terms of CPU, I buy that it's extremely low. But in terms of memory, right, like which is also a significant portion of that pie, like do you think?
Yeah, its memory overhead is likely higher, but again, there are probably opportunities for optimization there. I mean, generally, like an OS or any application, it's going to kind of fill. It's just going to fill whatever memory is there and just leave, old memory hanging around there. So, like, if it was actively trying to reduce memory usage, it could probably, an active application is ultimately going to push out all the old memory and kind of use whatever memory it needs to use.
Oh, right, never mind. Also, used and unused memory is the same cost.
Yeah.
So
I'll spend the last 15 minutes just talking about how we can use IT to make buildings green. So kind of using sensors, smart software, smart appliances, smart meters. Focusing mainly here on buildings, although there are other aspects to making society's energy use more green. So smart buildings, what are kind of the prerequisites here? So typically you need to obviously monitor energy usage, ideally at some sort of fine-grained level from each load, so each device in the building. You have to be able to control devices' electricity usage. You can automatically turn them on and off or change their power state similar to like what you might do with a server. And also potentially you might want to monitor its environment, so like what's the temperature, humidity. Obviously devices often do this too. To control their usage, are people in the building? Where are they? How many people are there? What are their preferences? Do they care to have the temperature raised a little bit? And then how can we do all this cheaply and reliably, and also kind of be aesthetically pleasing? So existing systems, I like to think of as kind of equivalent to mainframe computers back in 1960s. So like. This building and other large buildings, probably not your home, have building management systems that already have tons of sensors, and they're actually, doing some sort of control over like really old protocols, so like BACnet, LawnWorks, not really designed by computer scientists or computer engineers. So these are like mainframes that they're large, they're monolithic, they're closed, they're proprietary systems. You can't really, it's very hard to kind of interact with them. And they're also not efficient in terms of kind of how they collect data. So like, typically they don't collect really fine-grained data. They collect, relatively coarse-grained data, kind of just looking at kind of high-level trends in usage. And they don't have really kind of pervasive load control mechanisms, right? They just kind of control maybe parts of the HVAC system, or sometimes, you know, maybe some lights in the building. But it's not really kind of ingrained into the system. And different components typically are using different systems, so it's not well integrated. So in terms of discussing kind of monitoring and what's needed for that, so monitoring is possible at multiple levels of the wiring tree. So you can do like an entire building where electricity comes into the building. You can do it at each circuit in an electrical panel, or you can do it at each outlet, switch, or plug. So each of these kind of poses different challenges. And then one issue kind of with all of these is kind of how do you transfer the data in real time to a server that can do something with it. So ideally, really what would happen is that, you know, you would wire Ethernet in conjunction with the power line. I think in some buildings on this campus, they've actually done that. So they actually have Ethernet going into the electrical panel. Unfortunately, legacy buildings, they don't have this. And it doesn't really work for, like, you know, you don't necessarily want to wire Ethernet to kind of every outlet and plug in the building. Although, you know, getting into the electrical panel is nice. Legacy buildings don't have it, so kind of how are you going to do this? The main ways to do it are kind of either over the power line or using wireless. So wireless, kind of Zigbee or Wi-Fi, and then there are a variety of power line networking protocols, X10, Insteon, and HomePlug. Each of these kind of have their own limitations. So obviously with Zigbee and Wi-Fi, there are range issues. There are also reliability issues. So there have been some research recently on kind of how you can scale out, you know, kind of a pervasive power monitoring infrastructure in a large commercial building using kind of Zigbee type sensors. I mean, this actually intersects highly with sensor networking research because, you know, this actually is a type of large-scale sensor network. Has to use kind of mesh networking techniques because you can't basically get from necessarily the sensor to each base station in one hop, so you have to send them through other sensors. Requires careful placement of the sensors. And there's still bandwidth issues in terms of actually getting kind of readings at a really fine grain, like every second, every 5 seconds, every 10 seconds. Power line networking has its own issues. So kind of old school power line networking, X10 and Insteon, which is kind of transmitting data over the power line, are very slow. And the power line is kind of a broadcast medium where kind of every device can interfere with another device. So you kind of, the data rates here are much less than what you're going to get typically with wireless. HomePlug is kind of a newer power line networking protocol that overcomes some of these limitations and can send data at a faster rate. But it kind of has form factor issues when wanting to build it into a really small sensor and kind of put it in an outlet box. Okay. Wireless networking, in both of these, actually power line and wireless also are sensitive to interference or noise. So like for wireless, you know, if you put this thing in a wall, that's going to affect the wireless signal, right? For power line, actually, if you have a lot of computers plugged in, a lot of non-linear devices plugged into the power network, it actually affects, it interferes with power line networking. Okay, so there are issues here. So it affects the data granularity. So it's actually, you know, it's not trivial just to instrument a commercial building and get good data at a reasonable granularity. So this is not a trivial thing to do. There are a lot of issues here. They intersect with a lot of issues that people have looked at in sensor networking, and I think it was surprising to a lot of sensor networking researchers that they spent, you know, the early part of last decade kind of researching these outdoor sensor networks, and then they kind of discovered, oh, you know, actually we can't even do this indoors, kind of in a building. So there are a lot of people kind of looking at this kind of stuff. So actually this here is a electrical panel we instrumented as part of some of the research kind of I'm doing with Prashant and Sean and Sandeep here. So this is actually in my home. So this is these computers down here are little embedded Linux computers that have a HomePlug power line networking adapter built into them. So they these little CTs here actually are sensing power kind of every second on each circuit. And these wires here, going up to here, actually transmit that data over the power line to a server, actually here in this building, in real time. Yeah, so this is the device here. Of course, this device is, it's small, but it's not small enough to kind of, put in an outlet or behind a wall per se. Here's some of the sensors. So these are actually fairly passive sensors that just, use the Hall effect to wrap around. You wrap around each wire, use the Hall effect to sense current, the magnetic field, and compute power. They're, one benefit of this particular device is that they size the sensors for each breaker. So it's got 200 amp coming into the house, that's current, and then each breaker is a 20 amp breaker. So having appropriately sized sensors improves their accuracy. So there are a lot of actually sensors available on the market here. So we've actually, as part of our research, experimented with quite a few of them. So here's just some examples. So this is a Z-Wave smart energy switch. This is a wireless device similar to Zigbee. You can see this, it's not maybe very aesthetically pleasing. It's kind of bulky. It's probably roughly kind of this big. Doesn't really fit into a wall outlet fairly well. There are devices like this device here, this is the front, this is the back, that actually build this kind of functionality into the wall switch. Unfortunately, they, wireless doesn't really work very well for these devices, so they use kind of the slower, and the faster power line networking also doesn't work well, so they use the slower kind of power line networking. They actually can't get much data. They can't send much data over time. So you're talking about maybe a value every, if you have a large number of these devices, every 5 minutes to 10 minutes or something. It's kind of the granularity of data they can support. So the challenges here kind of, it's expensive, cost between 50 and 150 per switch or outlet rather than $1. It's intrusive, so they may not look very good. And it's unreliable, so there are very serious bandwidth constraints, actually just getting energy usage, doing good monitoring. Some alternatives that people have looked at that actually we're doing some work with. Collecting high bandwidth data at the ingress where the smart meter is, and then disaggregating that data into separate loads. So basically using a few well-placed sensors and knowledge of the devices in the building, basically analyze the good data you can get at the electrical panel to figure out what the other loads in the home are doing without having to actually place a sensor at them, because there are kind of fundamental barriers to actually placing sensors at every load. Okay, it does raise privacy issues that I won't really go into. So in terms of controlling energy usage, so you need some sort of programmatic load control. Some way to control a device's energy usage. So a lot of the switches I just showed here are actually external load control. So these actually have load control features in them, but it's external to the device. Okay, so generally this kind of load control can be external or internal. External means you're just cutting power to it, which may not be a good thing, especially if the device has no memory of what its usage cycle is. So preferable is kind of have internal load control that actually is intelligent, saves the device's state, kind of knows where to pick up, can alert you if when you're trying to turn it off potentially that it's not a good spot to turn it off. So you're actually seeing a lot of devices actually incorporate these kind of internal control switches, control mechanisms. They're not really exposed to programmers as of yet, but that's probably not far off. Generally, the other problem with external load control is it's kind of binary. It could be dimmable, like meaning that you kind of only provide half the amount of power to the device than it actually wants. But most devices aren't amenable to kind of only providing half the power they need. They need either all of their power or they need to kind of turn off. Unlike servers, which can scale their power usage, and then most devices aren't built to scale very well. Okay. Oh, one thing here too is, unlike monitoring, I mean, you need a way to like communicate with devices, right? To control them, to say like turn on, turn off, shift your load, whatever. But unlike monitoring, the kind of bandwidth constraints and the power constraints may not be as severe. Because to control something, you don't need that much bandwidth to kind of just send a message to it. Okay, so controls may be a little easier in terms of kind of the networking constraints than monitoring. So this is just an example of like, you know, some of the products coming on the market. There's a range of kind of smart appliances coming on that have Wi-Fi or other types of wireless networking capabilities built in. So this is an example of just a washer and dryer, kind of the app that communicates with it to kind of monitor it, turn it on and off. In terms of environmental monitoring, there's similar issues as kind of energy monitoring. So these are predominantly wireless sensor networks. This is an active research area kind of in the sensor networks community, like I was saying. And there are also many commercial products now available that can monitor various, you know, aspects of the home environment, including motion sensors, door sensors, thermostats. So with smart buildings, you know, the question is kind of how do we use these mechanisms? So I won't go too much into this today, but there are a variety of things you can do. Like if you have good monitoring, you have really good control, you know, you can provide recommendations via a smartphone, you know, telling people like, oh, you left something on, you need to turn it off. You can enable, you know, just kind of like that washing machine back there, a remote but manual control. So like you can, there's a lot of products coming to the market where, you know, the idea is that you have an app and you can actually control things in your home or program them in various ways, kind of manually. You know, you can do control. Or you can have, you know, automated scheduling policies that actually control loads based on a variety of different objectives. So some of the objectives you might want to optimize for, if you have, you know, solar deployments nearby, you might want to align your consumption schedule, you know, loads to align their consumption with renewable generation. You might want to schedule loads to lower your peak demand if your electricity company charges you a fee based on your peak demand. You also might want to just, you know, automatically turn things off, you know, when you're not home. You know, so similar to like a thermostat, a thermostat that like, you know, programmable thermostat that will lower the heat or the set point when you're not home. In this case, you might want to turn off, you know, various unused loads when you're not home if you left the light on or something. So a variety of kind of policies, scheduling policies you might want to implement. Very similar to the types of scheduling policies you might implement in an operating system. So I think that kind of concludes my time. So, you know, just as a summary, you know, talked about two parts: screening of computing, so a variety of different issues with the design of energy efficient hardware and software systems, primarily in data centers. And then computing for greening, so the use of IT for monitoring and controlling devices, and then the ability to use software to do power management for these devices. Any questions? Okay, I guess that's it.